Hi, in this video we are going to discuss the CDC solutions designs. So might be 5 or 6 solution we gave in this series of CDC solution designs videos. So there are almost 5 or 6 popular CDC solutions are there. So we try our best to have that check whether it is good or not, or what conditions we have to check for the designs. Okay, so the problem definition for the CDC is mainly when there is a two domain circuits like clock A and clock B, and we need to have the transaction of data between these. So in that case there is a metastability occurs due to the violations of the setup and hold conditions. So for that we cannot avoid it, but we can isolate it, or we can mitigate that metastability due to the this violation of the timing constraints. So for this there are some certain CDC solution designs, we can say, that take care this kind of data transaction from one domain to another. So in this video we are focusing on the two flop synchronizer. Mostly it is a very known to all designers, because everywhere, even though you can search it, two flop synchronizer, we assume that some earlier knowledge of this CDC, what it is, and what are the problems with that. Okay, so we start with this video with the two flop synchronizer. So the list of some of the common CDC solutions are two flop synchronizer, gray. This is used for the single bit. This is a gray code encoding used for the multi-bit. Okay, FIFO also we can use for the multi-bit. Handshaking protocols, then dual rate DDR interface, then asynchronous FIFO, and I think we need to add one more, that is dual port memory, you can say. Okay, so that might be not heard by you, but I use most time. So the criteria for the CDC check in this video, as well as in further CDC circuits. So the criteria is very simple. We try our best to transact some signal or data from slow to fast clock domain. This is one criteria, from slow to fast, and second is fast to slow. And if the data we received properly, so we can say that the CDC solution is verified. Okay, we are not much concentrated on the post synthesis. We are very much interested in the RTL level of check. So might be after the post synthesis it has some issue, but if we take care at the RTL level, I think it can be mitigated. Okay, so this is basic things. We have to check with the slow to fast and fast to slow. Okay, so two flop synchronizer is nothing but a cascade of two flops at the destination site, as seen in this circuit. Okay, so we are driving this with the clock B. This is clock domain B, and this is clock domain A. Okay, so this signal should be we can properly receive at this stage. Okay, so after checking this with the simulation on some iterations, I found that it is used for the suitable conditions when the clock A is slow and the clock B is fast. Okay, means this is suitable for this condition, and it is for single bit transfer from A to B. But the data get lost when the clock A has higher frequency than the clock B. Okay, so I do one RTL code for this setup, and I try my best to have this signal on this sig1. Okay, so the duration of this is very important, how long it logical 1 or 0 depending on the requirement. So the first case I discuss here, when the clock 1 is slow and the clock 2 is fast. In that case I send some signals like this is a signal. Okay, and as we've seen there, it will verify that it is lock here. Okay, so we get the Q1. So in this case, whatever we send, it is get reflected on the output side. But the condition is that the whatever we are trying to send, the signal should be enough pulse width with respect to the transmitting domain. Okay, so at least one clock rising will be occur, so that it will goes to the Q1 first, and then Q2, Q3, and at last it is the output signal. So it looks okay for me when we are trying to send data from slow to high. So when the case is there, like the sending domain has higher frequency and the destination domain has the lower frequency. So in that case, what I found, it actually lost the data. Okay, so due to the pulse width, whatever the pulse width, let's say this is a signal and the pulse width is not enough length so that it can lock at the receiving domain. Okay, so it is clear, we can say here these are the rising edges. So obviously this respect to the Q1 actually, because this is a signal from signal 1 to Q1, and then Q1 trying to latch in this is another domain. Okay, Q2, Q3 signal out. So with respect to this Q1, this rising is not appropriate for this pulse width, so it is missing here. Again it is missing here. So at some point we get one of the occurrence there, it will lock the logic. Okay, but it obviously it lose some data, so I don't think it is a good. So this condition is not good for the two flop synchronizer while transacting the data. Okay, so this is a code that I am referring. This is a signal that we need to transmit, and Q1 is our first flop, that is transmitting flop, and this is for receiving domain, always block. So this is very simple as according to the diagram. This is a test bench, and you can pause and you can get that things. Okay, and the another test bench I written for this one. So in one go I switch the frequencies like low to high and high to low. While doing the low to high, we satisfy the condition for the data. Okay, so it means that we can send the data from the slow to high frequency, and for the fast to slow, due to the width not enough to have that lock on that signal, so it lost the data. But the if we make some provision that if we enlarge this width, not the period of this one, almost 1.5 times or greater than 1 clock, then we can able to get that things done. Okay, I try to resimulate with the increasing the pulse width. Okay, so in that case I received the signals from the fast to slow, but the condition is that we have to have the pulse width more than the 1 clock period or 1.5 times the clock period of the destination. So in that case we are able to have that. Okay, so keep in mind that the double flop synchronizer is not for all the conditions. There are some drawbacks, and if we mitigate that drawbacks, then we can have that signals at the destination side. So this is at the RTL level, but while we are going for the post synthesis, there will be some changes, or what we can say that there will be some uncertainty at the destination due to metastability of the particular flops setup and hold timing constraints or conditions. So I hope you got this point regarding the two flops synchronizer, and please subscribe my channel and make comment and hit like button, so it will motivate me for the further videos. And one more, just we start with this two flop synchronizer. Okay, in coming videos we get this gray code encoding, and we can go with all these things, okay, one by one. So keep in touch. Okay, thank you, bye.